singularity and its types, and today we are going to start this Riemann theorem also. We have done singularity and its type in the previous video, but here are some other definitions for these types. First is removable singularity. If fz has an isolated singularity at z0, then the singularity is said to be removable if limit z tends to z0 fz exists finitely. So you just check the limit z tends to z0 on fz, so it should exist finitely for singularity to be a removable singularity, right? Provided fz must have that singularity as isolated one, right? Second, if fz has an isolated singularity at z equal to z0, then z equal to z0 is a removable singularity if and only if limit z tends to z0 fz exists finitely. Okay. Second, z equal to z0 is a pole if and only if limit z tends to z0 fz is equal to infinity. So if limit exists finitely, it is removable. If limit exists infinite, then it is a pole. Third, an isolated singularity that is neither removable nor a pole is said to be isolated essential singularity. Very fine. This is very clear. Alright. Let's move further. So the theorem named as Riemann Theorem. Let's start this. If z equal to a is an isolated singularity of fz, and if mod of fz is bounded on some dilated neighborhood of a, then a is removable singularity. What we have discussed in isolated singularity, that it is a alone singularity. And then what we have discussed in removable singularity in the previous video, whenever principal part contains no term, then z equal to the point, here point is a, so z equal to a is a removable singularity if the principal part contains no term, right? Okay, so what is given to us is, I am having an isolated singularity at z equal to a, and also mod of function is bounded on some deleted neighborhood of a. So here, suppose I have taken a point a, then this is the dotted circle is the neighborhood of a, right? I have made a small circle inside this neighborhood, z minus a equal to r, having the radius r, and I have taken radius so small that it is entirely contained in this neighborhood of a. The circle is entirely contained in the neighborhood of a. Now let fz be bounded on some deleted neighborhood of a. Now it is also given to us that this mod fz is bounded. So bounded means I am having mod of fz to be less than equal to m, alright, where m is the maximum value of fz on the circle mod z minus a equal to r. So I'm having the maximum value as m on the circle, and the radius r is chosen so small that the circle lies entirely within this neighborhood of a. Clear? Alright. Now what is Lorentz expansion? So by Lorentz expansion, we have fz to be equal to, yes, tell me, infinite sum an, very good, z minus a the power n, plus now the principal part, n starts from 1 to infinity, very good, bn, z minus a the power minus n. So first is your regular part, then is your principal part, right? And we also know that the coefficient bn is equal to 1 over 2 pi iota integral over c z minus a the power n minus 1 f of z dz. We need this principal part to be 0, right? That's why I have mentioned the coefficient bn over here. Let's take the mod of bn. This is mod of 1 over 2 pi iota integral over c z minus a the power n minus 1 f of z dz. which is less than equal to, yes, mod of 1 over 2 pi iota is 1 over 2 pi, because mod of iota is 1. So integral over c, this is mod of z minus a the power n minus 1. This is obviously mod of fz is less than equal to m. And then we have mod of dz. Clear? So this is equal to 1 over 2 pi. Yes. What is mod of z minus a? This is your circle. R the power n minus 1 into m into, yes. What is mod of dz? We will calculate this on the basis of this integration. So this is equal to, yes, m is taking outside, m over 2 pi integral, r is also outside, r the power n minus a, integral over c, this is mod of z. Now this is nothing but the circumference of the circle. So this is m over 2 pi r the power n minus 1 into 2 pi r, which is equal to 2 by 2 pi cancel. This is equal to m r raised to the power n. Now this mod of bn is less than equal to m r the power n. Now this will tends to 0 as r is tending to 0. So therefore bn is equal to 0 for all n, right? So if bn is 0, which means principal part contains no term. So principal part contains no term, which means z equal to a is a removable singularity, which means why I have taken r tending to 0? Because the radius can be very, very near to 0. As small as possible we can take the radius, because we need the point to be isolated, right? So that no other singularity falls in the neighborhood of that point. So we must choose r can be any real number or very, 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 very small, almost nearer to 0, right? That's why r is tending to 0. So z equal to a is a removable singularity, hence proved. Right, here the proof ends up. Next time we'll do some more theorems. Right, so just revise all this proof. This is very easy. And also revise all the definitions of the types of singularity in the previous video and also in this video, on the basis of limits also, right? Okay, goodbye. Have a blessed day.